everyone, myself Shruti Patil along with my teammates Pratham Regunwar and Saloni Bharadwaj would be discussing a project which is based on the effect of the CMOS latch-up by positive and negative voltage on VDD and VSS. These are the contents which will be discussed in the further presentation. Our principal objective is parasitic and process simulation in NP-NP structure using Atlas to find the effect of latch-up on VDD and VSS using curve tracing algorithm and prevention of latch-up in CMOS structure.
So before we get into the simulation data, we would like to cover a little about the literature review or the project overview. So in simple terms, latch-up problem could be explained as formation of a direct route from the VDD VSS to the ground terminal in our design, which could result into large current flow between our power terminal and the ground terminal. This could lead to excessive power loss. So latch-up was really an important problem in early CMOS technologies, but as we've developed with our technology, we are working on the same. So the things that have caused them to fail are sometimes the triggered voltage spikes on the IO pads or sometimes the ESG transmissions. Next. So latch-up is a condition that is the formation of a direct path between the VDD and the ground terminal. So a basic inverter is made out of two MOS devices, an NMOS and a PMOS. So well and substrate taps are used to bias the well to the VDD and the substrate to the VSS, and they are put close by to the devices but not necessarily in between the devices. So this generates into a vertical PNP device formation that is between the P plus N well and the P substrate junction, as well as a horizontal NPN device that is formed under the NMOS and not unlike PNP, which is formed under the PMOS. So in NPN device, the lateral N plus P substrate and N well junctions come into the picture, and they form parasitic bipolar junction transistors that are the reason behind the latch trigger. Next. So inside an N-well, a PMOS device is formed as explained before. So as a result, the BJTs are formed. So a parasitic NPN BJT has grown near the NMOS device with the emitter being the NMOS source, unlike the PNP device with the PMOS being the emitter. So both of these BJTs are coupled in such a way that they create a PNPN device, which could lead to the R-well and R-sub formation. Next. So the PNP device is normally in off state and there is minimum current or no current flowing through it. But the slightest of gate signal could lead into it getting triggered, and a large current starts to flow through it, and it continues to flow even if the gate signal is removed. So R-well generally ranges from 1 kilo ohm to 20 kilo ohm, whereas the R-sub depends on the substrate input. So assuming that the R-well and R substrate are significantly large so that they could cause an open circuit connection, this results into low current gains and this leads to power loss. So if we go on to our next technology, that is FinFETs. So FinFETs are three-dimensional structures with vertical fins forming a drain and a source. So the reason behind this was to help us with scalability, but this would also help us with the latch-up problems, as FinFETs and planar devices have similar issues with latch-up, but this could be resolved using the substrate density that could be altered for them.
So now moving on to the technical approach, we would like to discuss a topic that is CMOS latch-up by positive voltage on VDD. So in this, a DC ramp of P plus contact in N-well is used. So once the voltage on the VDD exceeds a certain value, that we usually keep it as a 5 volt. So on the N-well, the P plus well junction is forward biased and latch-up may be triggered. So now to trace out various IV curves and other curves, we can use curve tracing algorithm that is used for tracing out the complex IV curves. So to use it, we can use a solve curve trace statement to extract IV curves. Now in this, various parameters can be set, and we can actually see the latch-up characteristics can be plotted, and the behavior of latch-up on positive voltage on VDD can be seen. And to make effective and to evaluate latch-up, changes in N plus and P plus spacing can be done in mask view. Here are various Tony plots that we have extracted. So on the left hand side, we can see a CMOS structure, and on the right hand side, we can see I versus V curve. So as already stated, CMOS occurs as a result of triggering a parasitic device. So an SCR is normally off device in the blocking state, and in that blocking state, it is a high impedance path between the supplies. When triggered into its conducting state as a result of excitation and applied on the gates, the SCR is said to be latched. So on the figure right hand side, we can see the current to voltage transfer characteristics. And in order to bring the device out of its conductive state, either the voltage applied across the SCR must be reduced to a value, or we can like set the current, and we can reduce it to its holding below its holding current. So now we can see the left hand side curve represent the parasitic PNP bipolar action in CMOS latch-up, and on the right hand side we can see the flow lines in the latch structure. Now coming on to the CMOS latch-up by negative voltage on VSS. So it is same as the positive latch-up on positive voltage on VDD, but the difference is that in this N plus contact in the P well is used, and the voltage on the VSS when becomes less than 0 volt on the P well, so the there will be a forward bias and the latch-up gets triggered. Again, in this we use the curve tracing algorithm to trace out various IV curves. We can actually see the CMOS structure and I versus V curve that we have plotted out from the atlas, and we can see the parasitic NPN in CMOS structure and various patterns of the flow lines that are there in the latch structure.
Next, we'll discuss the factors for latch-up issue. The resistance of well and substrate are the key factors which are responsible for the latch-up, since they trigger the BJTs present in the CMOS, and the product of the gain of these two transistors should be greater than 1 in order to sustain the latch-up issue. Next. So these are the prevention techniques we would be using to resolve the latch-up issue. First one is the guard ring. If V out falls below VSS and the NMOS tied between the drain and the P substrate becomes forward bias, electrons from the drain begin to inject into the substrate and are captured by PMOS body, which activates the QP transistor. To break this chain, insert two sets of N plus and P plus implant on the P substrate and N well. This will gather the electrons injected from the NMOS drain and prevent the current from flowing from the NMOS drain to PMOS body. The QP BJT is no longer triggered as a result of this. However, if the guard ring is added, these holes will be gathered by the guard ring, and which will prevent the latch-up. Next. Addition of the well tap cells. To avoid the latch-up in the tapless standard cell, tap the N well to VDD and P sub to VSS. The figure depicts the cross-section of the tapless cell and the arrangement of a well tap cell respectively. By chopping the tap cell, we may improve the cell density. The well tap cells are arranged in a regular interval in standard cell row according to maximum distance rule defined in the technology library. Next. Isolation trench. In this technique, NMOS and PMOS have insulated using buried oxide and oxide trench. A horizontal buried oxide created deep inside and vertical oxide trenches are created later and connected both together to separate the N well and P substrate. The oxide trench are insulators in nature, and so the oxide trench stops the formation of PNPN device. A cross section is shown beside. Next. Epitaxial layer. In this technique, a low to P epitaxial layer grows over the P substrate. The P minus epitaxial layer provides a low impedance path for minority carrier, which prevents the latch-up triggering. A cross section is shown below. Next. So we can conclude from this that the latch-up curve trace method was an efficient tool for tracing IV characteristic, and we can use Atlas for more complex N plus and P plus layouts, and different prevention methods can be used to avoid this effect in CMOS structure.
So now talking about the projectas, these are the various projectas that was carried out with the whole team, and the remaining work and the challenges faced are the remaining work includes the final report presentation and the comparison of positive and negative DC latch-up for different N plus and P plus spacing. The challenges faced were debugging and modifying Silvaco Atlas code to get desired result, and the multiple tonic dots were being plotted in a single graphical window. But by studying more about Silvaco and the tool, how it works, we actually overcame these challenges. Thank you.
Thank you.